everyone, welcome to today's video. Today we are going to see how LLMs work. LLM stands for Large Language Model. LLM is like the brain of GenAI. There are many types of brain: ChatGPT, Gemini, Claude, DeepSeek, and Grok, to name a few. They all work on different types of model. ChatGPT works on a model named GPT. GPT stands for Generative, Pre-trained, Transformer. Generative means it generates new content. It can be an image or a video, painting, voice, or programs, which is coding. Pre-trained means whatever content is generated by GPT, it has to be trained on historical data. It can be the web, internet, books, and a lot of data which is available. So it can generate new images, videos, paintings based on the historical data. Now let's see what does transformer stand for. If I give a prompt to ChatGPT, "Hi, how are you?" The immediate response which we get from ChatGPT is, "Hello, I am fine." So this transformer is like a magic box. It does magic. It takes some input and transforms it magically to some output. A transformer can take a text and convert it into a modified text, or it can take any form of sound and it can create voice. It can take text as an input and create sound or music. It can generate music. It can take an image and convert that into text, or it can also take text and create an image. And this all came into existence in the year 2017 from a very famous paper named
Attention is all you need.
Attention is All You Need. As mentioned earlier, Google Translator is also a primitive type of transformer. What Google Translator does is it takes an input. Example, it takes something like a word hi in English, and if we ask it to convert that into any specific language, like in Hindi in this case, it'll convert hi into namaste or namaskar. might get a response in the desired language. So if you input hi in English and you desire the expected output in Hindi, you might get namaste or namaskar as an output. Transformer is designed to predict the next output. It can be a word or a letter. Example, if I'm entering a sentence, hi, I am doing, and the next word it has to predict. How the sequence goes is the first letter is predicted G, then the next letter GR, then that goes into the input, then the next letter GREA is generated, then that goes as an input, and finally, this process of generating the output create till a sensible output or a message is created which makes some meaning till the end of the text. Let's move on to the step two, which is tokenization. Tokenization is cutting into smaller pieces. Let's call it that way. Suppose you have time traveled and you are in the year 1990. You've been given an old desktop computer which does not have a mic, it doesn't have a speaker. Only thing this computer has is a keyboard. You've been given a task on this computer to teach the computer English language. You're aware that computers do not understand languages and anything what it understands is only numbers. So you try to teach the computer by assigning each alphabet a number, like you assign 1 to A, 2 to B, 3 to C, and likewise. Post that, you need to teach words to the computer, which is the step 2. For teaching the words to the computer, example, you need to teach the word cat to the computer, which is CAT. You combine all those numbers which you have assigned above, like 3 for C, 1 for A, 20 for D, and make it as a word. This process of assigning numbers to the alphabets is called as tokenization. You can assign one number for each alphabet, or you might want to combine two alphabets together. Out of this word cat, you can combine two alphabets together, CA together, and T, and make it as just two tokens, or it might be like 15 tokens for just a three-letter word. And this process of providing the numbers to the alphabet depends on the model. The numbers of token created for the alphabets depend on the model. Each model generates different size of tokens. So this tokenization, this process of dividing these letters and giving them numbers, so the more you cut down the word like C, A, and T, suppose I only give two tokens, but if I give CAT, I can give three tokens. CAT, I can give maybe two tokens for each six loop. So the more and more we start increasing the number of tokens, it will give more deep meaning to these words. And different models will have different types of tokens and different numbers of token. This process of providing the numbers to the alphabets is also called as encoding. or tokenization. And this is the step one for encoder in LLMs. So, encoder and decoder are two parts of LLM. We are talking about encoder in this video. Let's take it one more example. Suppose a new dog has come to a new home. A puppy has come to a new home, and this puppy is not able to understand what its owner is talking to it. But it has eventually understood one thing, that owner uses some specific words at certain times of the day. Whenever it is a meal time, the dog owner uses the word food. The dog has understood that food is related to eating, or hunger. Sometimes, instead of using the word food, the owner uses the word eggs, sometimes treats, and some different words. The dog is able to now understand that all these words, food, eggs, treats, are all related to eating or hunger and have a same semantic meaning. Whenever it's time for a walk, the owner uses the word walk, and the dog has understood that the meaning of walk is outside. And this process of understanding the meaning of words by the dog is called as vector embedding in transformer architecture. Let's take one more example. Example, there's a word cat, and cat loves to drink milk. I write the word pedigree, and immediately what comes to any human's mind is dog, because that's how we are trained to find out the semantic meaning of the words. If I plot the graph, the x on the x and the y axis, ideally it doesn't happen on the x and the y axis. It is much more mathematical, but just for understanding purpose, if we plot the word cat on the graph, we might get it here. And since cats and dogs are both domestic animal, the plotting of dog will be somewhere nearby here. Since the cat likes to drink milk, the plotting of milk will also be in and around the cat, but not in the same quadrant, but it would definitely be at the same distance from the reference point. Now, if I come down from the point of cat towards dog, and in the other quadrant, if I come down from the same distance as how much I came down from the cat to dog, exactly on the opposite quadrant, look where the dog is situated, exactly on the opposite quadrant, there's a high chance that I might get pedigree. And this can happen with all the words. We know that cats and dogs are animals, and there's a high possibility that the humans might have plotting somewhere nearby coordinates, but exactly in the opposite direction. So there's a high chance that man, woman, girl, boy, the plottings might be here. And if we exactly go in the opposite direction, same as how much we had gone from cat and dog towards their food likings, if we go to the exactly opposite direction, there is a high chance that you might be rice, dal, roti, sabzi, the food which human beings like. So when we saw the example of cat and giving the numbers as 3, 1, and 20, in ideal world it happens in a different way. So there is something called as vectors, and these numbers can be any digit, it can have different sign, it can be positive, negative, depending on what type of word that is. So example, the vector embedding for the word is like this. But sentences can change meaning if we have different, the words are kept in a different position. Like the dog chased the ball, and the ball chased the dog. These two are totally different sentences. So what solution has been given by transformer is that to these vectors they add another matrix which gives the position of the particular word. So when we do some mathematical calculations, the final output which we get after multiplying it to the positional embedding is a proper sentence.